Hydration is sexy.
Hey, y'all. How's it going? So, good day to you guys. Thank you guys so much for popping by. This stream's going to be a bit of an irregularity as opposed to like most normal ones, just because I keep talking about how I'm going to do a math stream for so long, and I realized that I'm not going to be really be able to get across what I want to talk about in VR. Um, I want to, but the thing is that the early math is much more complicated with like trying to draw what I'm talking about. But as we get further into math, I should be able to start explaining concepts in VR chat if I do continue along this path. However, I'm doing pretty good, Alpha. How about yourself? And that's great to hear, honestly, Colin. Can't see you? Yeah, we're just taking a second, all right? Um, however, as I was setting up, yeah, so this stream is going to be a stream where I talk about like a lot of the basics of mathematics that lead in towards calculus. And a lot of the stuff I'm going to be talking about at the beginning of the stream is going to be stuff that a lot of people really don't want to listen. I know math has a little bit of a stink to it for a lot of people. Sometimes you had a really bad experience with mathematics in your elementary to high school career, and it left a bad impression. And I want to try and like help you guys like understand the more mechanically enabled mathematics, like the stuff that's like more interesting to talk about because it has more fun applications, I guess. But yeah, quite the interesting stream concept. Exactly. Honestly, Vanilla, how are you doing, by the way? Well, if you're a good boy, thank you, Dirty. It happens. It happens. But yeah, so we're gonna be starting off doing some basic definitions, things you probably learned in elementary school. I need to do those things just because it's important that you guys like have that base concept understanding. I can't leave any holes, pretty much. So it's gonna be a bit weird. Doing really well, catching your stream while at work. Well, absolutely awesome to hear. By the way, if anyone is feeling especially interested in the stream and stuff, feel free to ask me any questions. I may not have the answers for you on hand, but I'm gonna try and get those out to you as quickly as I can when they come up. So yeah, let's go right ahead. I've got some Photoshop open, and I'm gonna be doing a little bit of conceptually organizing. So we're gonna be as a basic framework of what I want to try and get done today is I'm gonna be focusing a lot on ooh, you're in voice chat my server and we were possibly talking shit about really you're talking shit about me. Damn, I'm crazy. Okay, it happens, you know, like it's fine, it's whatever, right? um expect some shit in your mail. Okay, it happens, it's fine, it's whatever, you know, it's just chill. But yeah, no, we're gonna be starting off just going over the brief like understanding of like BEDMAS or PEMDAS, depending on what you're like comfortable with, just so I can go over the concept of like, oh yeah, this is multiplication, this is addition, this is like what we're talking about when we deal with these things. And then from there, we're going to completely ditch it. I need that when I talk about proofs, and I realize that like it's confusing, it's complicated, but I want to have that basic like there's something there, even though we're going to be overwriting a lot of definitions when we get to set theory. Calling you a naughty boy and how much of a cute bottom you are? Damn, that's unfortunate. That's very unfortunate for me, I guess, huh? But yeah. So let's start this off with the concept
The
of
fuck are you
mathematics.
doing, you silly fox? Hydrate, motherfucker. Drink some fucking water.
All
God
right,
damn.
all right, think easy. I understand. I understand the mood. Okay, absolutely. We'll start with the hydrate. But yeah, around these parts, we try and stay hydrated together. It's just as important that you guys stay as happy and healthy as myself. I got some water here today, but I'm always curious what you guys might be drinking. So feel free to join along and let me know. I'm gonna need to keep hydrated during this entire stream, so this is a great time. Here we go. Perfect. So we're gonna start off by yeah, it happens. But we're gonna be starting off by talking about the concept of mathematics, what mathematics really means to a lot of people. And mathematics isn't necessarily like a field too much in and of itself. It's more of a tool that we can use to understand a lot of other fields and sort of grow our understanding on a lot of other topics. So, for example, like, mathematics, sure, you have like things that you can learn about, like, oh, integration techniques, calculus, so on and so forth, adding, subtracting. But most of what math gives us is the tools that we can use for our life. Now, most people, obviously, you really only need to know like things like addition, subtraction, maybe even multiplication if you're like doing like stuff to do with money and stuff. That's fine. That's reasonable. If that's the level of math that's good for you, that's completely fine. Mhm. Let's do VAC. Oh yeah, VAC time. Let's go. But yeah, when we continue on though, prove mathematically that you're not cute. You can't. I won't even try because that's a very, very difficult proof, and I'm not even sure if there's any contradictions in there. So we'll have some issues. All right. No worries, potato though. But yeah, so we're gonna quickly start off by talking. Oh, Zero Tiger, thank you so much for the follow. Howdy, howdy. I'm Volpy, and we're here having a chill old time today, doing a little bit of mathematics. But thank you so much for popping by. How are you doing today? Yeah, so we're going to quickly start off by discussing the types of mathematics that you probably learn about in elementary school. So we are going to be focusing mainly on what does pi equal in numbers? Complicated, okay, complicated. But yeah, we're going to be talking about to start this off, I'm gonna increase my font here because that's a little bit better. Bed mass. Now, bed mass is one sort of abbreviation that we can use for this topic, but of course, now more math. It happens. It happens. This can also be abbreviated using PEMDAS, but they are functionally equivalent. Okay, basically, in Canada specifically, or at least Ontario, we learn bed mass, which is brackets, exponents, division, multiplication, addition, and subtraction. You're Australian, lol? Yeah, no worries. However, the other version, PEMDAS, is parentheses, followed by exponents, of course. Everything else is going to be pretty similar. Just the P stands for parentheses. M is multiplication, multi, div, add, and sub. Rect. So it's a very similar thing. You're taught BODMAS. Really? What is O for Caducean? Also, Caducean, howdy, howdy. How are you doing today? Oh my gosh. And Zero Tiger, first time chatting. Yes, thank you so much for the follow. I hope you're doing well. You remember PEMDAS? Yeah, so these are functionally equivalent because despite you crossing over terms for multiplication and division, how we deal with these sections, which we're going to cover in a second, is that the multiplication and division sections are interchangeable, and the addition and subtraction sections are interchangeable. You just need to make sure that you're traveling from the left side of an equation to the right side of the equation as you do those steps. Brackets of division, multiplication, addition, subtraction, and exponentiation is not explicitly included. Gotcha. That makes sense. That's understandable. So what we want to go into is what exactly are each of these things and how do we understand like what each of those topics are. So of course, addition is using the addition symbol to plus. I mean, again, I'm starting with bare bones. It's fine. It's going to be simple. It's easy. Okay. But addition is basically take two numbers. We're going to say, if we have numbers A and B, we're going to say A and B. We're using algebraic terms. This is going to be very common. I'm not going to try and use actual numbers as much as I can. Okay. But if I'll use numbers for examples, but I'm not going to use them for like anything else. So if we have A plus B, If we try and evaluate this is where we're going to use an equal sign right here, okay? So an equivalent sign is, we can have, okay, so we're going to start here. A plus B is simply an expression, okay? So an expression is something that you can evaluate on one side together as one thing. So for example, if I have 1 plus 1, since there's no equivalent sign here, we can only imply an equivalence on one side of a relationship to get you 1 plus 1 equals 2. All right. But addition has a understanding of, if you have two numbers A and B, they can be added together to equal some other number, C. C is going to be equivalent to A plus B. Now, there's a few different ways you can go about this. There's a lot of strategies you can use to do quick addition. However, I'm going to quickly talk about, if you have numbers, let's say we have 1, 2, 3, and we are adding it to number 4, 5, 6. Actually, we'll make these more fun numbers because that's more interesting. We'll use 7, 8, 9. If we're trying to add these together, an example of a possible strategy you can use is by lining up the different numbers together that are in the same place value. So if we add 1, 2, 3 to 7, 8, 9, we want to work from right to left as we get values to increase, because for this strategy to work, we're going to be adding numbers together and then carrying over the excess. So this I mean, all of you guys are 18. This is an 18 plus 3. We all know like what numbers come in what orders. It's fine. By the way, Rose Socks, hello, howdy. How are you doing today? So 3 plus 9 equals 12. So we're going to put the 2 from the ones column here, and we're going to add the 1 into this line here. 2 plus 8 right here is going to equal 10, but we're going to add that 1, so we get 11, right? And we're going to add that 1 up there. Then this is going to be 1 plus 1 plus 7, which is going to give us a 9. So it's an easy way to go through. You basically need to go line by line, starting with the 1s, 10s, 100s, etc., and just work. Avery, thank you so much for the 1,000 bits, bro. It happens. Thank you so much for the bits. I'm just doing math. We're just doing math. It's fine. Thank you so much though. And Caducean, also I'm doing well. About to pass out though. Just wanted to stop by and say hello. Absolutely, it's awesome seeing you here, Caducean. If you're gonna head to bed and everything, and like you want to stay by and fall asleep to some funny math because it's boring and stuff, like feel free. Okay. So, whoops, oh my god, I fucked up. Okay, this is fine. 1, 1 equals 2, 1, 9. Okay, there we go. So this is like a possible strategy for how you're gonna do it. Addition. You're just gonna add together numbers. Are you a teacher? I've been employed as an educator, but I'm not a teacher at the moment. Last time I was employed as one was like September, so it was a while back. Okay, it's fine. So yeah, that's the strategy we're going to be using when we're doing addition. Is I'm going to just refer to it as like, oh, you're just adding individual numbers together. We're going to call this the ones value. We're going to call this the tens value. We're going to call this the hundreds. It's fine. It's whatever. Later on, when we get towards more algebraic methods, what we're actually doing is, if we say A equals 1, B equals 10, this is place value, C equals 100, etc. This is the same as saying 3A plus, what's it called, 9A plus, 2B plus 8B plus 1C plus 7C, and we're evaluating this. So this is the kind of vibe we're going for, and this is sort of what I'm going to be working towards, if you guys understand. You're gonna make me go back to bed? Liz, go back to bed. Easy. But yeah, that's kind of the vibe we're looking at, okay? That's fine. Why math in the morning? Because Liz, it's the best time for math. And hello, Dildo. Howdy, how are you doing today? Dildo, you've been going through a lot of stuff, and I want you to know that we're here for you completely, okay? If you need to talk about anything, I got your back, all right? So this is addition. It's just a number plus a number equals a number. That's cool. Wonderful. That's great to hear. Oh my gosh. So next up, we're going to be talking about subtraction. Now, subtraction, I'm going to be using the new math definition for how you're going to evaluate subtraction. Again, we're not going to be evaluating exact numbers, but I want to just go over this because it's something that's like really prevalent in how people are teaching the math system in elementary, at least in the US. I don't live in the US myself, but I know that this is a big, complicated thing that a lot of parents have that's like, oh, you can't change math. Like, why are they changing math? This isn't how it's done. But I'm going to show you guys the new way that people do subtraction, which basically turns a really complicated subtraction problem where you have to carry values over and just do a whole bunch of complicated stuff into an addition problem that's really simple. Can we use imaginary numbers in subtraction? I mean, if you'd like, absolutely. We're going to be getting to imaginary numbers much later along the line, and that's probably going to be in VR once I'm done this like base level here. But subtraction is going to be given by the negative symbol, okay? And this is basically saying A minus B equals C. This is the formation of it. The negative, we're going to be talking about how functions work and why some of them are atomic and some of them are what's called compound functions. But we're going to get to there eventually, okay? Don't worry about it now. But yeah, let's say we have our numbers 1, 2, 3, and we're subtracting 7, 8, 9. Now, this is a really complicated problem, right? Because, I mean, we don't really know how we're supposed to be, like, getting to this point. Like, we don't really know how to, like, subtract a number from another number. Like, sure, you can borrow from, like, another place position and then work your way through. But the reason I specifically chose a larger number to be subtracted is we want to end up with a negative result. So, how we get through this type of math. Jesus, I remember how to do this by hand. No worries, Liz, it happens. I'm going to be showing you the easy way. So the easy way kind of goes towards the subject of how you're taught rounding in school. So get yourself to easier numbers that are easier to evaluate, and then work your way from there. So for example, 1, 2, 3, if we're trying to get to 7, 8, 9, right? Well, 123, if we add 7 to that, this gets us to 130, which is a nice number, right? We can work with 130 pretty easily. If we add 70 to this, which is actually a fun number, we can get to 200. Well, now we need to get 200 to 700 right here. So if we have 200 and we add 500, we get to a number 700. And then we just need to add 89 to this at the end. 789. Little cute sussy bottom. It happens. I like pause. Hello, howdy. So we've reached this final number right here. So now we should be able to kind of understand. What? Missed what you said before. Are you talking to me? Yes, still I was talking to you. Absolutely. Here to support you. So we've reached this final number and we've seen what numbers add to get to this last number. So now we can just reverse this and kind of discuss like in reverse. Like we've added these numbers together to get there, which means that 789 subtract the sum of those numbers equals 123. So that means that if we just add these numbers together, we get this result C right here. So C ends up equaling, I'm actually going to just line them up as a sum, but you know, it's fine. We're going to take 500. We're adding 70. We're adding 89. Oh my gosh. Avelita, thank you. Thank you for hitting me with the random shit. It's great. And we've now turned this problem into an addition problem. So we started with a really complicated subtraction problem that's honestly pretty hard to deal with, but we've rounded up our numbers to the nearest easy numbers to work with. If we're working in base 10, that's going to be tens. I'm so confused, but thank you so much. No, it happens. It's good. So if we had our 9 and 7, we're going to get 16. So that gives us a 1 up here. If we add these together, we're going to get another 16, which is a fun one. And then we add a number here, and that's going to give us 666. Wow, that's a very funky number. However, we've noticed that we started with a small number and we're subtracting a larger number. So what we're going to do here as a leap in logic, I could show you why like this is like the opposite way around, because you'd technically be starting from 789 and working your way backwards, but we always start from the smaller number, make it bigger. It's fine, right? Problem. I'm literally going to school and work now, Volpe. Where the hell have you been? Hey, it happens, Avelita. We're good. We're good. Nice number, yes. But because we started with a smaller number and we're subtracting a larger number, this is going to actually be smaller than this initial number, 123. But since we have 666, we're just going to add a negative symbol here, and we get negative 666. So that's just how we do results, is if the starting number is smaller than the larger number, we're just going to add a negative symbol. It's pretty easy right there. Yeah. Basically, the other way we could go around this to avoid just like fixing it. Like, oh, sorry. Where the hell have I been? I've been here. I've been here. It happens. Did I miss another one? Also, Wizard Wolf. Hello, howdy. I didn't realize you're here. Howdy. How are you doing? I remember doing something similar back in school and getting in trouble for it. Yeah, this is the new way teachers want you to learn, and this is the easier way because you don't need to deal with like subtraction itself. You can just turn subtraction into addition. Math at this time of night hurts my brain. It's a mood, honestly. You never see me. It happens. It happens. I'm just around, you know. I'm here, there, everywhere. It's a vibe. So yeah. We can have negative numbers. So this brings us into a more fun concept here of how our numbers work. We're not going to go into it. I'm just going to say that we have negative numbers, we get to 0, and we get to positive numbers. This is just how we're going to go. If we're adding, we're usually traveling to the right, and if we're subtracting, we're going to the left. All right. That's cool. That's fun. Math is math. Why change it? I hate you. I hate you, Potato. But yeah, this is the 5. Yeah, no, we're listening to Pink. It's fun. So that's addition and subtraction. All right. Well, now we're going to move into multiplication first, okay? Because multiplication is a more simple concept to understand, but when you get to like the end point for division, it makes more sense then. So if we start with multiplication, now some people are going to say, oh yeah, let's use an X and stuff like that. That's cool and all. You can do your elementary school multiplication. We are going to be using a circ dot. Basically, this is just the typical multiplication form. It normally dictates that you're using scalar multiplication in general. So this is going to be what's used for like dot products because dot products are scalar. And since we're using numbers on the number line, those are going to be scalar numbers. Elevated, thank you so much for the follow and first time chatting. Hello, Volpe. Yeah, welcome to the Foxverse. Yes. But howdy. Thank you so much for the follow. I'm Volpe. We're here having a chill time doing some math and staying wholesome with an ass to risk. Thank you so much for popping by. How are you doing today? But yeah, so multiplication is going to be dictated by A dot B equals C. Now, the main way that we're going to be looking at this is, I'm going to say here, for actual numbers, just use a calculator. Okay, it's fine. Just use a calculator. When you're talking about using variables, you're going to be looking at the numbers that are prefixed to these A's and B's. So honestly, it's like, just use a calculator. It's fine. The way we can understand this, though, in a more practical sense is we have A sets of B. So for example, if we have, I'm going to be using single digits here. I'm sorry. It's just easier for pictures. If we have like 3 times 9, then we're taking 3 sets that have 9 elements in each. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Another 3. 1, 2, 3, 4, 5, 6, 7, 8, 9. Another set here. And we have 1, 2, 3, 4, 5. 1, 2, 3, 4. This is a visual representation. It's fine, you know? Learning math, in my opinion, the lamest subject. Actually, science is better. Get to blow things up. Yeah, but math is a good thing for like describing things to science. And also, are you doing homework or are you educating chat? I'm educating chat because we're going to be getting through like some more complicated subjects. I'm doing the base bones right now. But my homework is not like this. My homework would make a lot of people's brains explode, and I probably shouldn't. So, yeah. But yeah, so this is going to be called repeated addition because we just want to add up our ticks in each of these. So if we count these together, we have 9, 18, 27. So 3 times 9 is 27. There you go. So we're using a calculator, but this is the kind of concept we're doing is we're repeatedly adding certain numbers together. So this is the same as doing 9 plus 9 plus 9, which is adding 9 3 times in a row. It's understandable. It makes sense. It's reasonable. So the same way as how multiplication travels in one direction, division is going to be its inverse operation. So if we have a times b equals c, then we also have that, if we have a times b equals c, we also have that a equals c divided by b. You doing master grade science and maths, so my homework will fry most for equals brains. You can understand the mood. I'm doing like a course on applied cryptography right now, and like the proofs involved in it are just it's fun. It's fun. It's a cross section with a master's course, so like I am doing basically a master's level assignment without doing the what's called capstone. So yeah. So we're going to be talking about division. Now, division, you can use a what's called a line, which is the normal way we're going to be seeing it. However, if we're actually talking about division in a sense that we're talking about one number divided by another number as a binary operation, okay? This is a binary operation, okay? We talked about an atomic operation and binary, okay? If we're using a binary operation, we're using the abolish symbol here. So the abolish, this is what you're probably going to like recognize if you're talking about division, okay? But an abolish is exclusively talking about the number directly to the left and the number directly to the right, okay? But a division symbol like this, we'll talk about everything on the top having a hidden parenthesis and everything on the bottom having a hidden parenthesis. It's fine. When we use the abolish symbol, we are talking about exclusively the elements directly to the left and directly to the right, okay? That's why, like, if you have, like, those, like, funky problems where, like, somebody says, oh, yeah, well, we have, like, 1 plus 2 plus 3 divided by, like, 7 or something. I don't know those, like, funky math problems and stuff. If they use this abolish symbol, it is exclusively talking about the left and right side of that, okay? We do not care about what's on the other side, okay? We don't care. I don't care, okay? I don't care. But, you know, it's a thing. And it makes me mad when people, like, don't treat the abolish with the respect it deserves, okay? We love abolishes, okay? It's fine. She doesn't care, exactly. But for division, if we have that a times b equals c, division's the reciprocal operation. So if we have a times b equals c, a is equivalent to c over b. Now, later on, it's going to matter what this division is like. However, the kind of topic that we're talking about here is that a is also equivalent to c times the right multiplication of the inverse of b. That's a lot of words, and it's going to come up later, but we're going to actually give you the foundation of why it matters where we multiply things from. But for now, division is just taking, okay, well, let's say we have 27 numbers, right? And let's say we're trying to divide it by 3. How many is going to go into each of those sections? This is the same thing as doing 27 over 3. And of course, as we saw up here, this is going to be, well, if we have 9 elements in each section, we can get it perfect. So that's fun. That's cool. That's awesome. However, when we have a number, like let's say we have 28 divided by 3, the 28 doesn't evenly go into 3. We want to, as a mathematical brain thing, we don't want to get an approximate value for this. We want to leave it as is, unless we're actually dealing with measurements, okay? So if we have 28 over 3 and we're talking about like 28 over 3 centimeters, yeah, get it approximation value. This is going to be something like 9.3 or 9.33, right? But when we're actually continuing to use mathematics and we want accurate answers, we want to leave this in its fractional form. Some people call this an improper fraction in elementary school, but that's a really bad way of describing it. Just because improper means that it's not correct. But you really need the math to be like in its improper form in order to actually continue and have accurate calculations. All right. So that's multiplication and division. Next up, we have exponentiation. So exponents. Now, exponents are shown as a larger base number to an exponent equals a value. So a to the b equals c. Now, what a to the b means is that we are multiplying a b times. So a times a times a times whatever a. And there are b elements here. Now, we're going to use a really simple example here. We're just going to say, all right, let's just do improper fractions, something like 3/2, 9/4, etc. Yeah, exactly. But we want to leave it in its improper form in most senses, unless we're talking about exact measurements. Okay? So if we have this b times multiplying a, that's going to get you what c is. All right. So for example, if we have 2 to the 3, that's the same as saying 2 times 2 times 2, which equals 4 times 2, which equals 8. Well, why are you doing math? Because I have to. It happens. You got to go. Love you guys. Yeah, no worries, Avelita. Stay safe, enjoy yourself, and have a great day. Redcoat, because math is important, and it's important to know math. So that's what an exponent is. And last but not least, parentheses. This is going to be very, very funny, but parentheses are just using brackets to surround values in the middle. What parentheses allow us to do is basically say, all right, well, do every operation on the inside of that in the order that's given. My lack of says otherwise. Damn. So, for example, if I have brackets a plus b, this is the same as what's it called? Adding a and b together, and then adding c if I have c in the end or something. So a plus b and then plus c. So if order matters, then the stuff that happens in the inside should happen first, and then stuff on the outside. That's cool. Multiplication. Sometimes we omit. Hi, Volpe. How are you doing? I'm doing really good, Volpe. Volpe, how about yourself? Oh my gosh, I'm just doing a lot of wacky math, so it's very fun. Sometimes we omit the c dot in the center and just say a b equals c. That is perfectly valid. You can do that as much as you want. When this doesn't work is when you're trying to talk about scalars versus vectors, and it's more correct to have the dot, but if you know both a and b are scalars, then you can just have them multiply together. That's cool. That's good. All right. So let's talk about bedmass. Bedmass is a topic that is a really fundamental thing. It's the order of operations. So for example, if we have this order of operations going brackets, exponents, division, multiplication, addition, subtraction, then what we want to do is if we have a large expression, for example, I'm just going to give an example up here. It's fine. Let's do 3 times a plus b over 2 times. I'm not gonna use. This is dumb. Oh fuck! I have a background. Oh my gosh! I'm not working on the background. Oh, I'm working on the background, bro. This is weird. This is terrible. This is fine. I'll just fix this real quick. And we'll just like say that this is 4 plus 8. These numbers are very specific that I'm using here, but like, we'll put a square here as well, just so I can have an exponent. All right, that's cool. No, we'll put the square down here. All right. So if we're going to be following our order of operations, we want to solve what's in the bracket first. Okay. So for this expression right here, it's going to be 3 times whatever 4 plus 8 is, which is going to be 12. Divided by 2 squared times 3. Now that we've evaluated this down to being a single value, we don't need to do any operations in the brackets. The brackets are meaningless from here on out. So from here on out, I'm going to omit them. Next up, we want to do the exponents. So in here, we're going to be doing 3 times 12 divided by 4 times 3, because 2 squared is 2 times 2, which is 4. Next up, we want to be doing our multiplication and division from left to right. Now, this is more complicated when you have a bar for division, but if we treat the invisible parentheses on the top and bottom, we can actually evaluate each of these individually. And we end up with 3 times 12 being 36, and dividing that by 4 times 3, which is 12. And if we do division last, well, now we have 36 divided by 12, which is 3. Now, this is functionally the way you do it, okay? Like, this is how you do it mathematically. There is a shortcut you can use, because when you're actually working on something like 3 times 4 plus 8 divided by 2 squared times 3, well, these 3's will cancel out early on. This is something that we can just do, because if we're if we have a 3 over 3, this is 3 numbers fit into 3 spots, so that's going to equal 1. So those cancel out. We also know that 4 is 2 squared, and 8 is 2 cubed, right? Wait, did I messed something up here. It's 36. 4 times 3 is 12. That should be 3. I messed something up here. And I'm very dumb here. That's 4 times 3. 3 squared. Yeah. Whatever. This is probably gonna sort itself out or something. I don't know. It's fine. Oh yeah, we're good. Okay, perfect. So we can actually do something called factoring. We can factor a 2 squared in the numerator, basically by dividing out 2 squared from each of these terms to end up with 1 plus 2 to the 1 in here, which we can cancel these and end up with 1 plus 2, which equals 3. There we go. We're good. It happens. Factoring is a topic we will cover a little later, but we don't need to know factoring to do set theory. It's a fun trick of the mind that once you get good at it, you kind of like just have better intuition about math. You just like, you do more math, you get more intuition, you can factor easier. You failed your algebra in freshman year in high school? Really? Damn. That's sweet. That's repeat. That's so unfortunate. But this is your first time chatting. Howdy, howdy. I'm Volpe, and we're doing a little bit of math today. But thank you so much for popping by. How are you doing today? So this is the basis of algebra. It's like, you know, you have an order of operations, and you're going to perform calculations in that order. That's cool. You can do that. That's awesome. Like that's fun. Awesome. Excellent. So now let's talk about proofs. Now, proofs are a menacing topic, okay? They are actually like, okay, I should, maybe if I create new, we don't want the background, we want it to be white. There we go. White. Perfect. Okay, excellent. You're doing well. That's great to hear. And this is why I didn't even consider going to anything other than trade school. It happens, Vessi. It happens. Should we take notes? I'm going to be posting these notes on my what's called Discord, so you don't need to take notes. Don't worry. It'll be publicly available, and also the VOD will be up, so you can understand it. So when we're talking about math is logical. It's a tool. Like, math is a tool that we can use to solve other what's called problems in other subjects. But that means that because math is a tool, we need to have it that math is fundamentally true, okay? So what we need to be able to do is take, oh, Cesar V, thank you so much for the follow. Oh my gosh. Yeah, I'm glad you could pop by. I hope you're like here ready to like, you know, have a chill time and things. It's vibes, whatever. But yeah, so we want to make sure that we can be able to prove that something is true using our base knowledge of math. So, the rule is first the parentheses, multiplication, and after division. You need to follow this rule. Yeah, basically that full T. It happens, yes. So yeah, from here, we're going to be talking about some different methods of doing proofs because some things have direct implication and some things don't. Now, what we want to be able to show is we have various types of operators that can show equality or some other like various fun things, greater than equal, less than equal. So we're going to quickly talk about what those types of operators are. We go into statistics. I need divine help for that class. Boots recommended I go into statistics, so I'm probably going to do that once I get to integration, which is probably going to be very soon. So when we talk about using an equal sign shows equivalence between two numbers, okay? I can use an equal sign here as a joke because that's fun. So if something on the left side of an equal sign is the same as something on the right side of equal sign, then those two things are equivalent, okay? Or sorry, are equal, sorry. If we use a triple equal sign like this, that's giving you a stronger knowledge about the internal form of that thing. Basically, you can say that, sorry, if we have a set that has like A, B, we're going to get into sets in a second. Don't worry about it. But if we have a set that's A, B, and we have a set that's A, B, B, sets reduce down. They're not unordered, okay? So sets are going to reduce down. This set right here will reduce down to AB, which means that these two are equivalent, okay? But because the values that are exactly inside the form of these two sets aren't the same, we can't give it that triple equals equivalence. So that's the two difference there, okay? You're going to integrate yourself some food? Yeah, do it. Excellent. So that's sort of what triple equals is. If we have a greater than, this means that the number that is on the what's called larger sides, so if there's a larger gap there, that means that the thing on the left side is larger than the right side. The other thing we can have is a less than, which means the left side is smaller than the right side. Sorry. My writing is notoriously bad. I'm sorry. It happens. You're gonna integrate yourself with some food? Yes, absolutely, Vanellope. Enjoy yourself. And Proxy, hello, howdy. Excellent. So these are the types of operations we're going to be using if we're trying to discuss the size of elements. So if something is larger, we're going to use greater than. If something smaller, we're going to use less than. If something is not necessarily always greater than, but can sometimes be equal, we add an equal sign at the bottom. This is strict. But if we have a less than or equal and greater than or equal or whatever, or sorry, greater than equal, less than equal, these two are not strict. Math stinky, damn, it happens. And for Raya, hello, howdy. I'm gonna just like, do this like, get wrecked, Raya. But useful, yes, absolutely. So these are the types of topics we're gonna be talking about here. Also, I should label this like, sorry, this is order of operations. And this one is going to be talking about proofs. Thanks for the shout out. Absolutely, of course. Of course, the Sammy clip. It happens, Raya. Your new free count's really cute. Thank you so much for being small and stuff. It happens. All right, so let's talk about different types of proofs then, using this as our knowledge here. So we're gonna there's some set theory we're gonna need to discuss here. We are going to be explaining set theory after we can explain proofs, because there's certain types of proofs that require set theory to understand, for examples wise. But at the same time, we need those types of proofs to like describe set theory. So that's why we need to touch on set theory in order to do those proofs. That's fine. All of your classes were modified in your high school career? Really? Damn. So what were they like then? So let's start off with a. This is the simplest type of proof here. Okay, y'all got snow over there yet? I think we're getting snow overnight tonight. So we're going to be starting off with the simplest of proofs, a direct proof. So let's say we have, let's say a number is even if it's 2 times another number. So for example, if n equals 2m, okay, then it's even. I'm also gonna say this arrow is implication. So this is an implication sign. So if n equals 2m, then this implies that n is even. This is a proposition. We're going to be talking about proposition statements in a second, but this is the proposition we're going to be trying to work with. So we know that the fact of n being double another number means that n is even. If m is, m is an integer. Okay, that's cool. We'll touch on integers in just a second. Okay. So this is the true thing that we know. Okay, this is something we know. So now what we want to do is say, all right, well, let's say prove the sum, or sorry, the sum of two sorry, I'm confused. Two even numbers is even. Well, a direct proof can be, well, if we have two numbers that are even, so let's say we have number 1 is equal to 2 times a, and number 2 is equal to 2 times b, then if we take n1 plus n2, this is equal to 2a plus 2b, and we're going to be doing a factoring thing from before, where we're going to factor out the 2 from each of these sides and add a bracket next to the a and b. So 2 times a plus b, and since we have a plus b right here, if we say that n3 equals a plus b, 2 times a plus b, then this means that n3 must be an even number, because if we say m is equal to a plus b, then n3 must mean that n3 is even. It's fine. It's whatever. It's cool. This is propositional logic, okay? It's fine. Some were very small in students because you had a hard time keeping up, and other students who could work twice as fast as you. I got you. And you're back from the depths of hell. What is that? What the hell is that? Is that math? It's math. Yeah, it's fine. So this direct proof right here, we want to have a explanation statement of this result at the end. So since n3 is of the form of an even number, therefore sum of two even numbers is even. There we go. So that's the kind of direct proof. Is like we took two numbers, we did an equivalence relation, and just worked our way down and found a result here at the end. We say that this is n3. And then we've directly proven that it is of this form of here of 2m. There's another step here, which is checking that a plus b is a number of the integers, but that's another thing, okay? Because I've had to do factoring so much here, I should probably discuss what factoring is, but, you know. Yeah, I'm going to be discussing factoring here. So, wait, what the fuck? That's weird. New. We want this. Great. There we go. Please, I'm doing it, Mr. Gross. It's fine. Shouldn't be in bed, but you got me hooked. Excellent, the Easy. Awesome. So what we're going to be talking about is the distributive property, okay, of mathematics. We'll talk about the we'll talk about the distributive property. Basically, what the distributive property says, this is giving me brain damage. It's fine. Just don't worry about it. You can tune out if you want. Like you're not being forced to stay here. So the distributive property basically says that if I have a number that is being multiplied, or sorry, if I have a sum in a bracket and we have a number that's being multiplied by that sum, then this is equivalently related to saying that we have a times the first element in there and adding it to a times the second element in there. Sorry. This is what the distributive property is of multiplication. Now we're going to be getting towards the Z of C axioms and also a lot of the fundamental like natural number and integer axioms, which will better describe what this multiplication is actually doing there. But we can say that the distributive property is just a multiplication fact of multiplying by a sum that is all together in one neat little bundle. We can also say that we have an associative property for addition, because this is another thing that we have in our normal math repertoire. For a number system to work, you need a distributive property and an associative property in most rings, but that's ring mathematics, that's fine, whatever. But the associative property is basically saying, okay, well, A plus B plus C is equal to A plus B, right here, plus C. This is what the associative property does. Oh my god, Blovey, thank you so much for the follow. You finally followed me. Hello, howdy, how are you doing today? Oh my gosh. Hope you're doing really well. I should give a shout out to sorry. I forgot, okay? There you go. Father Hegel, follow, okay, guys. You should follow Father Hegel, okay? And then you can also like you know, follow Blubby as well if you want, okay? It's fine. It's cool. People are cool. The commutative property is a fun one because it's not usually necessary. But when we're working in fields, we do have a commutative property. So it's good to know right now. The commutative property basically says that A times B times C is equal to A times B times C, right? No, that's the other order. Sorry. If we have A times B times C, sorry, commutative property is A times B times C is the same as saying C times A times B. We can reorder any of these in any way we want. So if we actually talk about it in terms of a binary operation, we can just basically say A times B equals B times C. That's good. Thank you. Sorry, I'm confused. I'm dumb. I'm completely insane. Okay, it's fine. I'm just like working my way through math, and it's like fine. Something we're going to be talking about later on as well is the different number systems. Now, for example, this is different depending on whether you're working with statistics or for mathematics or computer science. But the philosophy I use is basically we are going to say that the natural numbers right here, the natural numbers here, which is going to be shown by this n right here with the extra line in the middle, is the set of elements 0, 1, 2, 3, all the way up. There's an infinite number of these, okay? Don't have any questions? Because you're, yeah, it happens. I love math. Nice, Bobby. Excellent. There you go. Perfect. Math was hard for me because my dyslexia struggled in regular classes. No, I can feel that. The fun thing about math is that like when you get far enough into math, you stop like having to worry about like the individual like multiplication, like division, addition, subtraction, and stuff. A plus B squared equals C. How so? If I tell you my question, you won't understand. I mean, ask me the question anyways. It's fun. We say that this Z right here is negative infinity all the way up to -3, -2, -1, 0, 1, 2, 3, towards like infinity, okay? However, we can add a proxy to this Z and say, oh, if we want Z positive or negative, let's just say positive, for example, this is how we're going to get the positive numbers that are exclusively positive inside this element here. You can do N positive if you want, but we use Z positive because that's pretty accurate. And this is going to give us the numbers 1, 2, 3, all the way up to infinity. Okay? So if I reference the natural numbers, the integers and stuff. Oh, we're going to get there, Volty. Don't worry. We're going to get there. It's not something that's necessary right away. That's going to be something I discuss when I actually get to distribution in a second, okay? We'll get there, okay? Trust. Yeah, no, natural numbers, this N stands for natural numbers, this Z stands for integers, okay? And they're all going to be the whole number values that are either positive or negative, okay? We don't talk about any fractional things right here with these two number systems, okay? That's fun. Awesome. So, first following along the textbook, we're on theorem 1.23 on page 11. Oh yes, of course. The textbook isn't necessary for this course, though. Of course, I'm sorry that you guys had to buy it, but you know, like, get wrecked, scrubs. But yeah. Stefan Creative, thank you so much for the follow. Howdy, I'm Volpe, and we're here having a chill old time today, saying wholesome with an S to risk. Thank you so much for popping by. How are you doing today? Yeah, but I can translate the Arabic if you want me to translate the Arabic. What is a constant function? A constant function is we're not talking about functions yet. Okay, functions are very far in the distance. Oh, wait, is this math class? I thought this was lit. It is Rhyme. It is. Oh my gosh. A constant function is a function f of x equals c for a constant c. So c can equal 1, 2, 3, etc. It just means that any x you put in will mean that you get the same value out no matter what. Yeah. Joke's on you. I work at a college bookstore. I just hoarded my textbook. Oh my god. That's legendary. Okay, that's fantastic. But what we can do with our distributive property actually is if we have two numbers that are being multiplied together. So for example, we have A plus B times C plus D. This is an extension of the distributive property, okay? This is really messy, okay? This is messy, okay? It's fine. But if we can extend the distributive property to talk about any number of things inside of a bracket. I don't understand anything what you're saying. It happens. Don't worry, it's fine. Then what we can say here is we can actually do the distribution for each of these individually. So we'll have our A times C plus our A times D. And then we have our B times C plus our B times D. Now, this right here is going to give us the primary example to start off with understanding factoring, because when you can distribute something from two different multiplication terms, then you should be able to divide something out from each term. So, for example, right here, we have A times C plus A times D, which is the same as A times C plus D by using our factoring rules before. Okay? And this is added to B times C plus D. Cool. However, both these terms have the multiplication of C plus D inside of them. So we can factor out C plus D, and then we can say that we have A plus B left over. And this is distribution. And then this right here, this step and this step are factoring. So factoring is basically the reverse of distribution, okay? So if we have a distributive property, then we should always be able to factor out terms if it's properly distributed. My words in Arabic, you're in English. Yeah, I understand. It's fair. But yeah, factoring is always the reverse of distribution. If you want a more lengthy result, you want to distribute out, and then you want to factor back to a more simple result. That's sort of how you're going to tackle a problem if you want to, of course. But like, yeah. There are certain techniques for factoring, but there's very fun ways to go about it. I'm going to show you one real quick example. So if we have a plus b, and we are squaring this together, this is the same as doing a plus b, as you said, Volti, times a plus b, which gives us a times a term, plus an a times b term, plus a times b term, plus a b times b term, which if we turn this into exponents, we turn a squared plus, there are two ab's here, so we want 2 times ab plus b squared. So if we have something that's of a form of an a plus b to an exponent, it's going to be, there's an easier way to like try and understand things here, but we can find patterns like this to try and reverse factor out the results. If you want to go for like, oh yeah, I want any exponent for any a and b, well, this is where Pascal's triangle comes in, okay? Pascal's triangle is a fun mathematical thing where we basically say, all right, well, we have 1 and a bunch of zeros here, like towards infinity. And every next line is going to be the sum of the 2 values above it. So these are zeros. I'm going to neglect the zeros after this term. And 1, 2, 1, 1, 3, 3, 1. And we're going to expand that down, just like whatever. Now, the thing that you can notice here is that if we are multiplying 2 numbers together, or sorry, 2 binary values together, then we end up with a situation where this middle term right here is the sum of the terms above, which is the 1 and 1. Sorry, 1 and 1 is dumb, okay? We have 1a and 1b, so that means that the sum of the terms above are going to be 2 times the product of the 2, okay? So pretty much if we examine this as saying this top line here is row 0, 0, row 1, 2, 3, etc. If we take the exponent of the binary value, okay, and we find that row, these are the coefficients that are going to be used for
hydrate, you cutie.
function, or not the function, but the distributed value or expression. So for 2, we distribute this out to be 1 times a squared, and okay, sorry, I need one more thing here. There's one more thing I'm missing here. Okay, I'm gonna hydrate, but I'm missing one thing. Okay, time for me to drink. Yes, absolutely, it's gonna be time to drink. I'm getting a bit mixed up. I'm so sorry, guys. It's fine. But yeah, around these parts, we try and stay hydrated together. It's just important that you guys stay as happy and healthy as myself. I got some water here today, but I'm always curious what you guys might be drinking. So feel free to join along and let me know. So we're gonna we start with the it's probably easier to show with larger exponents or a sum symbol. I think a sum is applicable here. This is dumb. I shouldn't show this until I explain sums, like expand sums. But just know that the exponent is going to be decreasing on the a as you proceed. So this is a to the 1, and this is a to the 0. A number to the power of 0, so n to the 0, is equal to, you can guess it, 1. Because you don't have any of these things being multiplied together, which means that if you have like n times n times n times n, you have an implied 1 at the beginning, okay? And if we don't have any of these n's together, then that's just going to give us the 1 at the end, okay? So a number to the power of 0 equals 1. However, 0 to the power of 0 is equal to 0 because a base of 0 implies that you have that implied 1, but you're also multiplying it by terms of 0, which means that that's going to result down to 0. That's just a thing about mathematics that's like a funky one, okay? It's funky. There's discourse about that in high school when they like try and explain to you and like say, oh yeah, well like what if this and what if this, and it's fine. Ellie, hello, thank you so much for the raid. Howdy, I'm Volpy. Oh my god, to all of y'all raiders and such. I'm Volpy, and we're here having a chill old time today. It's staying wholesome with an S to risk. Thank you so much for popping by. How are you doing today? And Yuru, hello. Oh my god. Yuru, did you have a good time with Ellie? Was Ellie being cute and like slut or something? Oh. So this is a fun thing about like factoring, because like, you know, factoring is cool, okay? But I'll go into factoring techniques later on. We don't need to know about factoring later on, but we just know that factoring here is the opposite of distribution. So if I had 2 times a plus b, that's going to be equal to 2 times a plus 2 times b, but we can reverse that operation, okay? So we factor. Cool. Now, we have 2 more main types of proofs here. So if we have an implication that A implies B, this means that if A is true, then B is true. Sorry, wait, I need the truth table. Hold up. Zero, zero, 1, 0, 0, 1, 1, 1. So 0 implies 0. This is true because 0 implies anything. 0 implies 1 is true. 1 implies 0 is false, and 1 implies 1 is 1. Okay, so we'll just turn the zeros into falses, and yeah, okay. Didn't talk about. Okay, we're not going to talk about truth. Okay, for a second. We'll go into it much later, but yeah, it's Boolean logic. It's Boolean arithmetic. We don't want to talk too much about Boolean when we're talking about these proofs, but because proofs are talking about the truth of things, it becomes a necessary thing to just talk about it. But pretty much, the next type of proof we're going to be doing is a proof by contraposition. So this is proof by contrapositive. Boop, boop, boop. So contrapositive basically says, if we have A implies B, then taking the opposite of B. So this is, we're going to call the opposite of B not B. Okay. Is going to imply not A. This is an inversion of logic. If we look at the truth table, we can actually see why this happens. So I think I should show you the truth table. A is a factual statement. B is a factual statement. They are prepositions, okay? So this implication is a prepositional statement, okay? So A can be true, B can be false. A can be false, B can be true, so on and so forth. So if I show you A not A, B not B, and then A implies B, and not B implies not A. So implication is a fun type of concept here, because basically 0 implies anything. Or sorry, false. I mean, I shouldn't use numbers, okay? False implies anything. Truth implies truth. So using these two things, truth gives implies truth is true. False implying anything is true, but truth implying false is false. Basically, if something happens and something else doesn't happen, then there can't be that implication relation. All right. So we just want to say 0, 0, 1, 1, 0, 1, 0, 1. Not A means that we're... Fuck, I'm using numbers again. Okay, I'm sorry, guys. False, false, true, true. Not A means that we're going to get true, true, false, false. And then we want a true, false, true, false. The reason why we're doing this order of true, false is that we're pairing a true to every false and a false to every false. And then we have a true to every true and a false to every false. And then right here, if we reverse this, it's going to be false. It's going to be true, false, true. So A implies B means that, let's take a look at A and B. So false implies anything. So these are both going to be true. Truth does not imply false. So this is going to be true and this is going to be false. Now, if we look at not B and not A implication, if we have true to false is false. True to true is true. False to false is true. And false to true is true. Yeah, true, false. Yes. And you'll see that these kind of have like an inverse relationship where whenever A and B is like opposite. So if A is false and B is true, that's going to have the opposite relation of if A is true and B is false. So these two falses are perfectly paired up to one another. There is a direct relationship between these two falses happening. And because we can pair up each of these truths together in some other way, it doesn't matter what fashion, these two contrapositive things, basically if B is false implies A is false, is equivalent to saying that A implies B. Okay. This is a fun one here. So contrapositive, basically the kind of idea behind there is, let's say that I gotta think of a good example. All right. Well, let's say that on the topic of this n is even thing, let's say that again we have our truth statement that m is an element of z, and n equals 2m implies that n is even. Okay, this is the truth thing. Now let's try and say that will our homework have to be done in LaTeX, or can we submit handwritten documents? You can submit in either LaTeX or handwritten. However, LaTeX is going to be graded in a much easier fashion for us, so you might get more feedback on your assignment. No worries. That's a good question, Avery. Thank you. Let's try this out for size, okay? Let's say that this thing right here. Wait, are we getting homework? Yeah, you're getting homework. Obviously, of course, yeah. This right here says that if n equals 2m, because 1 cannot be divided by 2 evenly, then this means that if n equals 2m plus 1 for some m, then this is odd, okay? Cool. So, let's try and consider that the fact that if we have two numbers, prove if n squared is even. N is even. Yeah, this is a good one. This is a good one. This is an easy one. Good morning, Bob. Yes. Sorry, I don't do homework. Yeah, no worries, Ryan. You don't need to do the homework. It's not grade for a high percentage of your mark. You can replace it with the final exam. It's fine. But Mirson, howdy. How are you doing today? Oh my god, I'm gonna get you a shout out. Sorry, I got a little sidetracked here because I was trying to figure out what a good example here is. So if n squared is even, n is even. Well, if we take the contrapositive, let's say that n is odd, prove that n squared is odd. This is easy enough to do. Because now we can square something that's like whatever. So if n is odd, then n equals 2m plus 1, right? Which means that n squared equals 2m plus 1 times 2m plus 1, which equals 4m squared plus my brain is actually fried. 4m plus 1. And we can see here that if we factor out the 4 from the 4m from here, we can get 4m times barely functioning right now after doing late night work and sleeping 4 hours before early morning meeting. Oh, I feel that. Times m plus 1 plus 1. And here we have that 4m is just 2 even numbers, which means that if we have m plus 1 times 4m, actually, I should only factor out a 2 because that's fine. That's sufficient. If we take m squared plus 2m as being an integer, and we multiply that by 2, this means that this is an odd number. So n squared is odd when n is odd. So by contrapositive, n squared is even when n is even. Contrapositive is good for a lot of situations where like it's a more complicated way to prove one direction, because it's not simple to just like do a direct proof. Because I'd have to, if I was trying to prove that if n's even, n squared is, which it's more complicated there. It doesn't work as nicely, okay? Yeah. So contrapositive is a bit weaker, but it's easier when you're trying to like prove the reverse thing. Lost Fables, hello, thank you so much for the 10 bits. Howdy, beautiful wolf. How are you doing today? Yeah, so that's contrapositive, okay? So contrapositive is a fun one. It doesn't get used too much compared to a lot of other types of proofs. Direct proofs are always the easiest. If you get an assignment that gives you a direct proof on it, like you are golden. Like things are going to be so easy. Oh my gosh, you're going to have a great time because like logically, as long as you don't lose track of things, you'll be fine. Good thing though, I just talked to my boss. I'm pretty sure my PTO is a go. Let's go. Yo, pop off. Oh my gosh. So this is going to be proofs too, because this is going to give us a lot more understanding here. And this is going to be the fun one. Okay. So we're going to just talk about a proof of contradiction. Okay. All right, guys. Guys, we're introducing rational numbers. Okay, it's gonna be fun. Rational numbers are cool. So rational numbers. Okay, rational numbers are shown by this Q. Okay. All right. Rational numbers. Okay. And they are formed of basically any A over B, where A and B are in, we'll say Z. There you go. So that's what a rational number is. It's an A over B. Okay? So contradiction. We are going to suppose that if we have the square root of 2, so contradiction is basically say, all right, suppose the opposite. So I'm going to try and match form of what I was doing in the proof here. Let's think. Contradiction is basically saying suppose the opposite. So, for example, I'm going to describe this through the example, but we're going to go back to the beginning at the end to try and understand what it is. Okay. Um, but we want to prove root 2 is not rational. Okay. So this is going to be a interesting topic here because like we know that if root 2 is rational, which is the contradiction, so we're going to suppose root 2 is the opposite of what it is. So we're trying to prove that root 2 is not rational. We're going to try and say, what if it is rational? So we're going to say, suppose root 2 is rational. And we're going to get to a contradiction somewhere. So the first step here is we say, all right, well, root 2 is rational, so it's equal to sum a over b. Cool. Well, now we can say, all right, well, let's just square both sides, right? Because we're working with a weird root on the left side, so it's probably easier to work in the what's called straight numbers, like whole numbers. That's the word. So this is going to be equal to a squared over b squared. Ayo, math stream? Yes, Ritzy, absolutely. We can now multiply our b squared over to the side right here and say that 2b squared equals a squared. All right. Oh my gosh. What's the next step, bro? Oh my god, what is it? Oh my god. Is it auto find math relaxing? Perhaps. I'm just like I'm crazy, okay? Oh yeah, okay. This is easy, okay. Oh, Cedric Fox, thank you so much for the follow. Howdy. I'm Volpe, and we're here having a chill old time today, staying wholesome with an ass to risk. Thank you so much for popping by. How are you doing today? All right. Okay, so the step right here, because we're talking about even odd numbers, then this implies that a squared is even, which is cool. Okay, a squared's even. Awesome. Watching math gives you the same as those satisfying videos. Really, Shadowpod. Excellent. So if a squared is even, because we proved back here that, back here we proved that if a squared or if n squared is even, then n is even. So this tells us that a is even. Oh, and Tantrum Dog, thank you so much for the follow. Howdy. I'm Volpe, and we're here having a chill old time today. From the last slide. Staying wholesome with an S to risk. Thank you so much for popping by. How are you doing today? Oh my god. So A is even from the last slide. Okay, that makes sense. So A is equal to 2m. That's cool. And because 2b squared equals a squared, then 2b squared equals 2m squared, which equals 4m squared, 2b squared, which equals 8m squared. No, 2m squared. And then that means that b equals root 2m. All right. That's cool. Okay. Um, but we also know that 2 divides b squared, so b squared must also be even. So that means that this right side needs to be even right here. So uh, since b squared even by this line right here, we don't need this last line actually. This is useless. I understand nothing, but I watch anyways. Excellent. This tells us that b squared is even right here. So b squared even. Then that means that a and b must have 2 as a common factor. Can both be divisible by b, or by 2. And we need one more supposition here, is suppose also root 2 equals a over b is in lowest terms. There we go. That's the thing I was forgetting. I'm sorry. Buster Stoat, thank you so much for the follow. Howdy, howdy. I'm Volpe, and we're here having a chill little time today. Staying wholesome with an ass. To Risk, thank you so much for popping by. How are you doing today? So this is in lowest terms, but because a and b can both be divided by 2, we've contradicted this statement right here. So that means that contradicted this. So because we've reached a contradiction, then this means that this section right here, it also falls and fails to be properly correct, which means that root 2 is rational is false. So this also implies that root 2 is irrational. Boom. Or not rational. Cool. Perfect. This is a proof. This is a proof. This works. So we're going to go back to the beginning. So the contradiction that what contradiction does is assume the opposite is true. So if we're trying to prove that root 2 is not rational, then let's try and prove that it is rational and show that we've reached an issue that causes it to not work out. And if we get to that position, then we know that because that contradiction comes up in the specific case that we have done the opposite of the preposition or proposition, then it must be true that the proposition that if we use the original proposition, then that must be true. Complicated words there, but just assume the opposite and show that it contradicts itself. And so therefore the opposite's not true, so the original words had to be true. It happens. It's fine. So that's a proof by contradiction. There's more proofs that are involved in a lot of like set theory related stuff, but there's one last one that is the killer for a lot of people, okay? So this is probably the most common when you're using infinite sets and when you're talking about infinities, and it's the one that's probably the hardest to wrap your head around, but I'm going to try and discuss it here. So proofs 3. We are talking, of course, about, if you guys are the mathematicians here, you know what proof we're talking about now. This is a proof by induction. So, induction. Oh, we love induction. Induction follows a very simple set of rules, okay? So we, in a situation where we have a base case, okay? We say that the base case is true. We can check that the base case is true by direct. So we want to do a direct proof to check that the base case is true, okay? We also suppose that what's it called? Okay, okay, oh my god. So this just says that p at 0 is true or something. Or okay. P at n is true for n constant. So the way we're describing this here is basically n equals like 1 or 2 or 0 or 3 or 1,000, okay? It can be a number, okay? We can do another direct proof here. And the next thing that we do is that if p, we want to check that p at n plus 1 is true if p at n is true, which is another direct proof. So this is our base case. P of n is true for a constant n. We also need to prove that every subsequent number is true if the previous one was. Okay? And then by this logic, then for every number above this base case, P at n is true. So hell, what's the general theme of explanations? Is it different archetypes of proof? Yeah, just different archetypes of proof. I'm just showing like the kind of topics you want to go into and just a quick example. The most important thing is I'm going to be doing proofs when I start talking about more advanced subjects. So I want to make sure that people understand the basis of what these proofs are and why you're actually proving something. Does that make sense, Splickroom? If you're experiencing any what's called Mangel amnesia and stuff, don't worry. Feel free to say, actually, that's this is more correct, because I'm completely fine with accepting criticism. If you have any questions, feel free to ask me. Sure, thanks. Yeah, no worries. Absolutely. Yeah, so if n is true and every subsequent number is true if the previous one was true, then P of n is true for n greater than equal to base case. So that's a pretty fun one here. The traditional example that we normally talk about is, what's it called? Let me think of a traditional one, because the two ones that come to mind are the one that talks about just strictly all odd numbers are of the form 2n, or sorry, all numbers of the form 2n plus 1 are odd. But then there's also the one that deals with the what's it called? What's the sequence? The 1 1 2 3 etc. Like the sum of previous terms. Bro, I'm going blank. I'm sorry. We'll go for primes are infinite. That's an advanced one. We don't go into that one, because if primes are infinite, we need to like start talking about some advanced factoring, and we're not there yet. We haven't reached the point where like we're talking about sets yet. So the Fibonacci, thank you very much. There's 2 B's in Fibonacci, right? Damn, it happens. Right? Yeah. So yeah, we'll go for this one. So show that all numbers n equals 2m plus 1 are odd. All right, cool. Well, we can suppose that we're gonna add this n element of natural numbers. Okay, because you just got here, Slickrim, I'm gonna just quickly show you the natural numbers we're using are starting from 0. Okay, not starting from 1, because we're using the positive integers to describe 1 through infinity. Okay. So the base case that we want to do here is the lowest possible n. Okay. So our lowest possible n for our base case. That's a beautiful, gorgeous Volpe I see. Yeah, Spikestone. Hello, howdy. How are you doing today? For lowest possible n that we have n equals 0. So base. I'm gonna do prove. Base n equals 0. So if n equals 0, then let's check what's it called? Let's check that. Or sorry, m equals 0 for n element of n. My bad. Bro, I'm cringing at myself. I'm actually dumb. Wait. Bro, I'm dumb. I'm so dumb. I use LaTeX, okay? It's fine. It fixes my mistakes. I'm actually crazy, okay? It's fine. But yeah, so n equals 2m plus 1 for all m element of n. So if we have m equals 0 as our base case. So I'll write base case. Then if n equals 2m plus 1 equals 2 times 0 plus 1 equals 1. 1 is odd. All right, we're good. We got 1 is odd. Okay, that's fun. So if we take so the next step here is we want to try and like form this into a inductive statement. So the inductive statement is the part that really makes people have a lot of issues. But what we can say is, well, if one number is odd, okay, well, we know that if you add 2 to an odd number, you're getting to the next odd number, right? So let's say that if 2n plus 1 is odd, 2m plus 1 plus 2 is also odd. Makes sense, right? Because you're just adding 2 to the original odd number. And we can just quickly check to make sure this is correct by saying, all right, well, 2m plus 1 plus 2. This is equal to 2m plus 2 plus 1. Remember, we're talking about how the distributive property allows us to, or sorry, the associative property allows us to rearrange addition terms. All right. So the associative property allows us to rearrange this 2 with that 1. So now they have a 2m plus 2 plus 1. And this is equivalent to 2 times m plus 1 plus 1. And if we say m plus 1 is equal to like a letter, I don't know, we'll just say like a, then this is equal to 2a plus 1, which is odd. That makes sense. That's logical, okay? So because every what's called 2m plus 1 term, or sorry, because every 2m plus 1 term is odd, and adding 2 to those also makes it odd, then simply adding, or sorry, bruh. Sorry, brain thinky go hurt and stuff. I was doing the wrong order of logic, but yeah. Yeah, so because adding 2 is odd, sorry. The wrong order, I think. Yeah, I definitely did. Well, to be fair, honestly, you can do it in the other order. This is just reverse induction. It's fine. I mean, it's not like I'm doing like some random like strong induction ass shit, right? It's fine. But don't worry, it's fine. It's cool. That's chill. I'm just gonna leave it as is. It's fine. But yeah, no, because we've proven that every adding 2 to each of these is odd. Then if we add 2 to this base case, then that makes it odd. And so by adding 2 to every 2m plus 1, so this implies that all n equals 2m plus 1 plus 2 are odd. And then we can just say that we have a base case of 1 starting that implies this section right here. And then from here, we're following dominoes falling and... Yeah, sounds good. And distribute. Yeah, that makes sense. Which means I should be using a different variable in here instead of m, and it's fine. It's whatever. It's cool. See, this m plus 1 equals a thing here should have been, I used this m being a plus 1, and then I show that you can form this 2m plus 1 plus 2, and then you can reverse it down. Which I guess I'll fix it. Ugh, this is fine. Yeah, we'll fix it real quick. That's cool. Because I'm working on the background, it's really annoying, but it's fine. Yeah, it really is. It really is. All right. Like, the more trivial you get, like, honestly, the easier it is for, like, somebody to disprove it if you, like, are saying one small thing wrong, as you have to, like, keep adding extra words to, like, try and make sure things are being said correctly. So if we say that m equals a plus 1, then if we have 2m plus 1, this is equal to 2 times, what's it called? A plus 1 plus 1, which means that this is 2a plus 2 plus 1, which equals 2a plus 1 plus 2, because we're abusing properties. And because we've gotten back to this section right here, then we know that if m equals a plus 1, or more so that the next number after a is m, gets us this plus 2 in the end here, then we can say that all n equals n 2m plus 1 plus 2 are odd, which means that we can simply keep adding 2 to this original n here, the space case. Customer for you're officially lost. Don't worry, Vanilla, it's fine. This section is not important. It's more so to, like, help activate for the next section, just for the proof sections. I'm actually probably going to get caught up on my word when I start talking about the Z of C axioms, but we'll see. We'll get there. Yeah, so because of all of these being odd, then this means that starting from n equals 1, and then adding 2 each time, gets us the form n equals 2m plus 1. Again, the variables I'm using here are really, since I'm using a trivial proof, the variables I'm using, I got mixed up somewhere in the middle, and it makes it more difficult to read. I'd lose marks on this for an assignment, that's fine. But adding 2 each time is of the form n equals 2m plus 1, and is odd. So that means that n equals 2m plus 1 is odd for all m element of natural numbers. There you go. Bro, I'm actually crazy. It's fine. We're good. Easy. Fantastic. Hi, Volpia Woo. Hello, Yeti. Howdy. How are you doing today? So yeah, induction is the one that's, like, really hard to get your head around, because induction is the type of proof that you always use when you're dealing with infinities or repeated patterns. It's really effective for a lot of combinatorial solutions. But at the same time, induction, because you're dealing with infinities as a newer math student, you might be more like afraid of using induction when it's probably the easiest one to use. We have another form of induction, which is strong induction, which basically just is another form of like incremental, but it's basically saying base case, and then you also have the n greater than n2 greater than n1 implies something, blah 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 blah, and then you just like, I'm not going to talk about strong induction. It's just that strong induction is sometimes easier for skipping steps for induction, because sometimes in regular induction doesn't make sense. It's fine. It's whatever. Okay, let's not talk about induction. Okay, it's fine. We're good. All right, so we've talked about order of operations. We've talked about what the operations are, how they work. We've talked about the types of number systems we're going to be building in a second. We've also talked about the different types of properties that are in some number systems. The commutative properties, again, not always in a system, but we'll get there eventually. Sorry. Also in here, we've talked about different types of proof: direct proof, contrapositive, contradiction, and also inductive proofs. There's more types of proofs, of course, but this is a good starting off point here. So let's get involved. I have some notes, because I took notes in my set theory courses. We are finally talking about set theory. Set theory is fun, okay? Now, we aren't going to be talking too much about like all of the different types of axioms, because there's the ZSC axioms are very intense, and the proofs behind a lot of things are very rigorous, and it's not something I want to be teaching to an introductory math group, okay? Just because like a lot of you like don't do math traditionally, so it's like I don't want to scare you off by doing like really intense proofs that go really deep, okay? So this is going to be starting to overlap with my last math stream when I was in VR chat. So we are going to start off with very basic things, okay? A set, by definition, okay, we're gonna have a set definition. A set is set theory is fun. Let's keep that quote. We might come back to it. Yes. A set is a collection of unordered elements, of unique unordered elements. I'm not going to define collection, because of course we just want to like have it be simple, like easy to understand. It's fine, okay? Unordered elements. So, for example, I'm going to be using S a lot when I'm talking about what a set itself. I'm going to be using A and B as constructs for sets. But for example, S might be, we use a brace right here to try and show like what's inside a set. But a set could just be like a set containing star, moon, and like, I don't know, like stick. We're gonna make this more like a funny symbol. That's cool. All right, cool. It's snowing where you live. Nice, Via Mike. Let's go. So notice that these are all unique unordered elements. If I, as earlier when we were talking about like equivalence versus what's it called, equality. When we're talking about sets, we can describe a set as being, I'm going to use numbers here to like describe things, 2, 3. But this set is equivalent or is equal to 1, 2, 3, because we reduce down the non-unique terms. But the important thing is that these aren't equivalent, because one technically has a different structure to the other. Okay. I'm going to be using equivalence and equality interchangeably here, but just recall that these are equal but not equivalent. So that's fine. It's fine. It's whatever. It's cool. So, first axiom of set theory, all right? This is fun. All right. Existence. So, the axiom of existence basically says that there exists a set S with no elements. Sorry. Yeah, there exists a set with no elements. Okay, yeah, perfect. Okay. Now, elements are the values that are inside a set. I didn't say what elements are. They're just the values inside the set. It should be apparent. It's easy. It's whatever. Okay. In terms of math notation that we use, basically, for all a sorry. Okay. Oh my God. We're going to say that there is a universal set, okay? U. This is the universal set, okay? This contains every element, okay? So A is an element of the universal set. There exists, there exists S, a set S. Whenever I say S, I'm going to be implying there is a set S from here on out, but I need to say it once for understanding. Such that A is not an element of S. And this means that basically S contains no elements. Basically, since U has all of the element, okay, E is element of, okay, basically saying it's in the set, okay. So if A is in a set, okay, bro, I'm set theory is not fun. This is funny. Yeah, so if A is in the universal set, there exists a set S such that A is not an element of S. Basically saying that for all A that are in every possible value you could choose of A, this empty set S contains none of those A. That's the axiom of existence. That's that. Cool. Awesome. Extensionality, okay, is the next one. If two sets have the same elements, they are equal. Same elements, they are equal. Now, the reason why we can talk about this is, if you remember up here, the set is a collection of unique unordered elements. So if they have the same elements, then they must have the same set of unique elements. And because they both have the same unique elements, then they must be equal. Remember that a set is unordered, so it doesn't really matter the order you put those elements in. They're going to still be equal, okay? So this means that if we have like 1, 2, 3, this is equal to 3, 1, 2. But also this also says that if we have 1, 2, 4, this is not equal to 1, 2, 3. Cool. That's That's extensionality, okay? That's extensionality. It's fine. It's easy. It's just saying like if you have the same things inside the set, then they're equal. If you don't, then they're not equal. Nice. There's not really any sort of like proof we need to discuss here, just because that is common sense. Like these are axioms that we're trying to like. These are the base axioms, okay? However, there's something that comes from these two axioms that's like probably important to talk about. And the important thing to talk about here is the uniqueness of the empty set. We need to be able to show that the empty set, which we're going to signify by this O with a slash through it. We want to prove it's unique. So the important thing here is we want to be able to prove that this empty set is unique. So no matter what set we choose, if it's empty, it must be this, what's it called? This empty set. So what we want to do is basically say that, well, we're going to call, this is the axiom of EX. This is EXI. Axiom of EXT. So by the axiom of existence, so AXI, we know that the empty set exists. Okay. Cool. Because there is a set that has no elements. That makes sense. That is reasonable. Okay. This is what the axiom says. Next up, we just need to prove that it is unique because we know it exists. Exists and unique. Okay, cool. Bro, what the fuck did I do here? Just gonna scribble that out and just say existence. Okay, cool. And now to prove it's unique, let's consider, we're gonna consider sets S1 and S2, okay? Basically, we're going to, consider their, math terminology, okay? We're gonna say it properly. There exists. This is the same thing as writing this like backwards E symbol. Sets S1 and S2. Such that both S1 and S2 don't have any elements. Now, to prove uniqueness, we basically are trying to show that S1 must be S2 at this point. But if they're both empty, then if every element of S1 is in S2, they must be equal by extensionality. But they both contain no elements, so that means that we do know that every element, the lack thereof of elements, S1 in S2, and so S1 equals S2. So it is unique. This is a pretty like straightforward proof. It's not too involved, but involves the existence and extensionality and tells us that the empty set is unique. That means that later on along the line, if we ever come into a situation where we're talking about the empty set and we come into a point where, oh yeah, we actually need two different empty sets. Well, now we can do a proof by contradiction and show that, oh, because we got two different empty sets later on along the line in another proof, then because the empty set is unique, then this is a contradiction. And so, you know, we can solve other problems based on this. It's fun. It's a cool one. Now, oh, this is going to hurt a lot. This is going to hurt a lot. This is going to hurt a lot. All right, guys, we are going to be talking about comprehension. Now, comprehension is a really, really fucked up kind of description here. But this is an axiom schema. What that means is that it can be used to build an infinite number of axioms based on the logic that it implies, okay? So, for example, let me just make sure that my mouse is not going to appear. So this is the axiom schema of comprehension. All right. And we're going to call this ASCOM. Okay. This is just going to be fun. And basically says that, let's suppose we have a property P of S is a property of S. Then, if we have any set A, any set A, there exists a set B such that, oh my god, oh my gosh, I'm actually crazy. If S is an element of A, I need to say if an, okay. Tylenius, hello. All right. So if and only if, I'm going to quickly touch on this right here. If and only if means that if A implies B, only if B implies A. So you need to prove that both A implies B and B implies A. That's fine. Hi, hello. So we call if and only if because it's just like, you know, the double if, okay? S element of B. And for all S P of S is true, subset. That's not an element. It's subset. Teaching math, yeah, just a little. It's subsets, bro. I'm dumb. Okay, bro. Subset. My bad. Okay, fuck. This makes me really mad. Okay, it's fine. I'm bad at this, but it's cool. We'll fix things up. We'll fix things up. It's cool. We're cool. This is too hard for you? It happens. It happens, hey. But thank you so much for popping by. It's your first time chatting. And as well, Fury the Wolf, thank you very much for the follow. Spartan followed me again. Wow. But thank you so much for popping by. Howdy, howdy. I'm Volpe, and we're here having a chill old time today. Doing some math and staying wholesome with an ass to wrist. Thank you so much for popping by. How are you doing today? No, no. And I reverse this. Good, that's great to hear. Excellent. Oh my god. It doesn't matter the order, but logically it should be this way. Subset B, subset of A, and for all S, P of S is true. What's the math equation? There is no equation. This is the fun part. We're talking about axioms. Axioms. Holy shit. Axiomatic math. These are just base building blocks. And then we can also show that for all P of S, and a set A, then, so we use a colon for then. Or sorry, such that. There exists B equals S.
Oh my god, it's hydration time.
Such that give X. There we go. Got it. We got it. And yeah, it's fun. Water, yeah, hydrate, yeah, excellent. Thank you. Thank you so much. All right. Around these parts, we try and stay hydrated together. It's just important that you guys stay as happy and healthy as myself. I got some water here today, but I'm always curious what you guys might be drinking. So feel free to join along and let me know. Let's go right ahead. All right. So we're going to be starting to talk about functions of sets. Holy shit. Okay. We wanted to talk about pair union and power set. Okay. So the pair axiom. It means that if we have sets S1, S2, so for S1, S2, then we have S3 consisting of exactly the elements of S1, S2. And so basically we say that didn't realize I was going to learn math. That happens, Wolvers. But thank you so much for popping by. Hello, howdy. How are you doing today? Because it seems exactly S1 and S2. So if we have for all S such that S is an element of, oh my god, this should be little s, so I'm just gonna make it smaller, such that S is an element of S1, and we are going to use the intersect right here. S is an element of S2. So this basically says that, or sorry, this is the union, sorry. Wait, this is intersect. What the hell? It's whatever. Basically, oh, I used to drive tow trucks, so I'm better at math than most, but I don't know what this is, lol. Hey, it happens. We're doing some basic set theory right now. I should make a pinned message that explains what we're doing, but like, this is fine. Implies that S is an element of C. So basically, the pairing is like, what's the What's the pairing? What's the symbol for it? Is it add or no? It's just C equals AB. There we go. Or S1, S2. That's it. That's fine. And C should be S3. Okay, this is fine. We'll just make that S3. That's what pairing is that you can combine two sets together to make one bigger set. How's my day going? My day is going fantastic. I'm just doing some math in the morning on stream because I'm actually crazy and insane, and I don't understand why people even watch this, but it's fine. It's cool. Next up, we have union, which is basically... Okay, so pairing is the elements of both of them. Union combines the sets. All right. Give me a second. Give me a second. I gotta think. I gotta think. Doing math in the morning equals good? Yeah, it's fine. Nope. Reese, what's up? Hi, hello. Health brain exercise. Yeah, exactly. I have to do a lot of math tonight, so it's like, it's fine. All right. The writing I wrote for my notes here makes things really complicated. So instead, I'm going to be discussing union as basically saying, if we have for S1, S2, S1 union S2 consists of all the elements of S1 and 2. And then this should be and S2. So pairing is the intersection and union is the union, which is fine. It's fair. Yeah. All right, yes, that's union. Okay, perfect. Okay, now we can move on to power set. Okay. I could prove uniqueness of pairing, uniqueness of union and stuff. It's fine. I can even prove that this B right here in the comprehension is unique. But those types of proofs are more so left as proofs that like build up from like the previous axioms. You can do those as your own. They can be left as an exercise to the reader. But power set is a fun one, okay? Basically, we say that for every set S, P of S is a set of all subsets of S. Cool. Basically, we can, the power set of S, we can select any number of elements from S and make a new set from it, and that is contained within the power set. So proof as left as an exercise to the reader. My favorite words to hear. Exactly. I'm so happy I managed to say that for the first time, like for real, you know. Is the mapping going well? I think it's going pretty well, yeah. So if we select any like elements of S, S1 through Sn, Then S1 union S2 union S3 ... union Sn is an element of the power set of S. We can select any number of elements. It doesn't really matter how many. We can select none at all, and that's part of the power set. The empty set is part of the power set of a set. Cool. So we can just say note empty set element of power set of S. Cool. Easy. We also have like intersection and difference of sets. Basically, intersection is like only elements in both S1, S2. So basically, S1 intersect S2. And then set difference. Okay, I should actually give an example for each. Fuck. Okay, 1 second. I need examples. 1, 2, union. 1, 3, 5 equals 1, 2, 3, 5. For pair right here, 1, and let's just say this is 2. Basically, we just have a set of 1 and we have a set of 2. I can say this is like 1, 1, 2. Yeah, it's just how we can pairwise order elements. Okay, it's fine. That's what pair is. Okay, it's cool. P of, we'll make this like a small one. My friend Helmio told me he doesn't understand the math, but likes to listen to your voice. Kind of sus, not gonna lie. Maybe sus, but maybe not. I mean, Harisayo, we're always having a chill time. But thank you so much for popping by. How are you doing today? I speak and it's fun. So I don't expand this too far. I'm just gonna do 2 elements. No pick, no. Oh my gosh. If I had 3 elements, it would be 2 to the 3. There'd be 8 numbers I'd have to do. I'm doing it. Oh god. No pick, no proof. I mean, we're doing proofs right now, so it's fine. This contains the empty set. It contains the set consisting only of 1. That was a really bad brace. The set consisting only of 2. The set consisting only of 3. The set consisting of 1 and 2. The set consisting of 1 and 3. The set of consisting of 2 and 3. And the last set is the one consisting of 1, 2, 3. You're mesmerizing Hey with your math. It happens. I'm so sorry. But yeah, doing math in the morning is good, though. Yes, absolutely. It's a 5. It's a 5. So that's a power set. And then the last intersection here, if we have 1, 2, 3, intersected with, let's say 2, 3, 7. This is equal to taking the things that are in both of the sets, 2, 3. You're studying programming on applied math as part of uni, but you don't remember anything what you're doing, or even if you like saw it ages ago. I learned this in my first year algebra class. This was my first lesson. This like entire like set of axioms was my first lesson in my first math course in university. It was intense. It was crazy, but like, I don't know. We the way my university works is it's really rigorous in its math. So every single student needs to like really learn the like depth of set theory in order to understand the calculus that they're learning at the same time. So it's fine. I'm trying right now, the process of my teaching right now, I am basically trying to show set theory, okay? And then from set theory, we can start talking about the constructions of number systems. And then from the construction of number systems, we can talk about how functions work based on those constructions. And from there, we can talk about sequences. And that's where we're heading right now. So yeah. Set differences are basically saying that set differences are, we'll say S not S1 is all elements of S. Without S1. Elements in S1. The most common situation where you're going to have an S not S1 or something is usually when you're talking about the real numbers without the, what's it called? Rational numbers. Whoops, my slash was the wrong way, bro. And this just indicates that you're talking about irrational numbers. So ones that can't be displayed as what's called A over B. Basically. So this is the normal kind of situation where you'd use like the set difference. Set differences, we try and make sure that the larger set, the smaller set contains exclusively elements in the larger set. But if an element is not contained in the larger set, but it's in the smaller set, then like you just ignore it. It should be fine. Yeah. So let's talk about constructions of natural numbers. This should be fun. All right. Natural numbers. So first things first, we're going to be using our sets to describe what natural numbers are and how they can be formed inductively. So what we're going to do is say, all right, well, what's the most fundamental thing that we can talk about our natural numbers with respect to our sets? Well, we saw that our natural numbers start at the number 0 and they increment by 1 each time as you go up. Okay. We can also note here, where is it? Sorry. That the empty set exists. The empty set is a set that's empty. There's nothing in it. So what we consider with our construction here that we're starting with is 0. And for 0, we can say that the empty set is the only set with no elements. So we just say that 0 equals the empty set. Cool. That's fun. For 1, we're gonna consider putting exclusively numeral elements that are part of the natural numbers inside of a set. So what we're gonna say is, oh, just on making a steamer. Nice. Damn. Okay. Excellent. Fantastic. We're going to say that because we're using the natural numbers 0, 1, 2, ... Then let's start with this lowest number here and just say that 1 equals the set consisting only of 0. Cool. Excellent. Now we can say, okay, we have our like little base cases, fun vibes, whatever. Let's consider that the successor of x. So if we say that sorry. Oh, sorry. Though I weakness. Okay, I got you. Good luck with math. Yeah, absolutely. Okay, yeah, no worries. If we consider that for like the nth term, let's suppose that x equals n. We can say that the successor of x, which is normally written as math ASMR, yeah, just a little. Fuck. 1 second. Let me check the proper notation because I've forgotten. Because I haven't like. It's s. Okay, perfect. Successor of s of x, s of x. Can just be x unioned to the value x. Basically saying that if we have two, or sorry, if we have the successor of one, sorry, so the s of one, for example, is equal to the set for one, which is 0. And this is union with 1. I'm sure that some of the Fourier reviewers would love to get ASMR Fox during Valentine's Day when you would explain Fourier transforms. I think Fourier transforms are probably like the most fun thing to explain, but in order to get there, we need to get through the entirety of limits, sequences, limits, calculus, integration, series, that kind of stuff. And then once we're there, we're actually able to like talk about fun series, which we can use with Fourier series and possibly Fourier transforms. So this equals 0, 1. So we say that if the successor of x is just this union right here, then for x equals n, then we can just say that n equals the set of elements 0, 1, 2, ... all the way up to n minus 1. And that also makes it so that the s of n equals a set of 0, 1, 2, ... until n. Havla, hi. I once calculated the minimum amount of time required to get 1 million points on Twitch. Really, Dracion? How long is it? So we can literally just say that this is an inductive set. We can keep doing a repetitive set here. So this s of n can continuously keep happening. So let's say we want the set of the number like 255. That's just going to be numbers 1 through 254. It's just worse. About 8 months. Is that 8 months straight then, huh? And CMYK, hello, and Gonzalo, howdy. How are y'all doing today? Oh my gosh. Yeah. So this leads us all towards the axiom of infinity. This is a really, really funny axiom because basically the axiom of infinity says an inductive set exists. And remember, induction is when we have a set that basically is self-replicable. So we have a base case being true, meaning the next value exists, meaning the next value exists, so on and so forth. So if we have a base case of n equals 0, which is the empty set, then for the natural numbers, we can say this is an inductive set because, we're just continuously performing this successor operation on the previous value to get the next value. And so on and so forth, blah, blah, da, finally, Femboy teaches math. Yeah, it happens. And are you infinity? Because I can watch you endlessly. Oh my god! Wow. So yeah. But if we consider like the axiom of extensionality, I'm going to say this right now. And the proof again is left to the reader, because I'm not going to go over it, because this is like, it's going to be a lot of very small incremental inductive steps, and I don't want to do too much induction here right now, just because it's a lot of writing, and you guys are probably going to forget what I'm just talking about, the main subject. But basically, the important thing that you guys want to solve, if you want to, is that n by the axiom of extensionality, ext, is unique. All right, cool. Fun. Ooh, Fluffy. Hello, Drac Reaper. Howdy, howdy. How are you doing today? Thank you so much for popping by. How are you doing? Hope you're having a good time. But what's really cool here now is that we have a series of sets, 0 through n. My name's Sunset. I'm trans F to M, and my pronouns are he, they. I'm a fox hybrid. I'm also a furry. Well, howdy, howdy there, Sunset. How's the boy doing? Thank you so much for popping by. How are you doing? And thank you for the follow. Again, howdy, howdy. I'm Volpy, and we're here having a chill old time today, staying wholesome with the asterisk. Thank you so much for popping by again. Same to you, Jack Reaper. Okay. You're Fluffy. All right. But now that we have like all these numbers 0 all the way up through n, all the way to infinity, we can say that that is a proper ordering. So now we've reached the point where we are now able to order pairs of elements and we can say that n is simply a set of ordered pairs of 1 oh my god. Sorry, 0 set of 0. Sorry, the empty set, my bad. The pairing of 1 with the set of 0, comma, ... And this is a very, very fun thing. What are your pronouns, Wolfie? I use she, they. It's awesome. Ooh, thank you. Yeah. So this is a cool thing, is that we now have ordered pairs. Oh my gosh. Now, I wasn't trying to get to this point, obviously. Impossible. Like, I'd never try and get to a point where I'm talking about ordered pairs, because remember, sets are unordered collections of unordered elements. But now we've reached the point where, oh boy, we've got a set of ordered pairs, and those ordered pairs are unique each in and of themselves. So now we're reaching the point where now we can have a relationship between one value and another value. Now this is very, very fun, because okay, this is really dumb. Okay. Okay, I should talk about Cartesian. I should talk about Cartesian projects really quick. This is hard. Box segment relationships between values. Ooh, I know, right? Did you just say fun? Yeah, fun. Absolutely. This might help me in the future. Not gonna lie. It could. It could. It could. This is like the base understanding of vibes, but that's fine, you know. All right. Well, we can also say that we have Cartesian products. Oh boy. Basically, if we have sets x and y, and so I'll just say Cartesian projects. So if we have sets x comma y, then all right, I should make that capital Y. Bro, this is dumb. You're wondering to be a math teacher, IRL? Nah, never. I'd never be a math teacher. I'd only be an educator if I ever felt like it. Then x, and we're actually introducing our first like cross multiplication here. Holy shit, we finally reached the point where we can start talking about like vectors with the use of this. We're not going to talk about vectors yet, but we now have the tool set to talk about vectors. This is a Cartesian product. And this is defined as x cross y is equal to the set. Okay. I mean, you're a Fox math teacher. Foxy and variables, you know, or any for maths and vectors. Yeah, exactly. Precisely. Okay, so we're using x and y, so I guess I'll just use like z element of the power set of the union of x and y. So this is basically saying, all right, we're selecting one x and one y. And this is going to be such that w equals a pair xy from that combination with x element of x, y element of y. There you go. That's a long one, but that's fine. Imagine somebody saying, I showed you my vector. I showed you my eigenvalue. Please respond, Uwu. All right. We did it. We reached this point. So let's start talking about relations. Huh? So, all right, boys. If we have two sets x and y, then we have a relation, a binary relation from x to y is a subset of x cross y, basically the Cartesian product. So the main reason why we want to use Cartesian products, okay, let's talk about the Cartesian plane. So let's say we have x and y being like the sets of all sets in the natural numbers. So let's say that x equals the natural numbers and y is equal to the natural numbers. This is a fun situation here where if we take x cross y, we get this cool looking grid right here, which goes from 0 to 1, 2, 3, 4, 5, 6, 7. Okay, that's a lot of numbers. I don't want to do that many numbers. 2, 3, 4, 5, and then we'll just have dot dot dots. And we actually create a cool grid right here, which basically just forms an entire grid of possible values along here. Now, again, we can subdivide this more when we actually like get smaller divisions between like elements inside the set we're basing it off of. But this is forming, using a Cartesian product, something that looks a lot like the Cartesian plane. If you remember, Cartesian plane is what you use when you like draw graphs. It's basically the plane that's like this, where you have x going in this direction, y going in this direction, and you draw some funky graph. This is the Cartesian plane. But that is formed using a Cartesian product of real numbers with real numbers. For now, we only have natural numbers, though, so we're going to have to make do with that. However, right here, this is an example of a relation. If you take a binary relation x cross y, sorry. Sorry, a binary relation, sorry, binary relation of x to y is a subset of x cross y. What about poly relations then? Yeah, I mean, poly relations, you know, they kind of vibe, you know. But do you like monotomically increasing functions? Oh boy, those are fun, right? So, a relation R is a set of ordered pairs. Such that X is an element of X and Y is an element of Y. We did it, boys. We did it. We have a relation. We have what R is. Now, let's consider what a function is. So a function F is a relation such that, oh my god, excellent. It's, oh god, math. Yeah, it's Levain. It happens. Function F is a relation such that F of X is an element of Y and X is an element of X. So we have a ordered pair of X and F of X. Cool. Functions. We did it. Boys, we did it. Now, what is F of X? What is a function? Well, let's start talking about what types of functions exist. Functions. All right. All right, boys. I have more notes here, please. All right. So, because the X that we're using is going to be a unique subset of the elements of X right here, then we're actually only allowed to have one unique X, or so one unique F of X for each X. So, if we try and take a set X and lead that to F of X, if we have like 3 points here, and we have like, I don't know, 4 points here, if we try and pair one of these up here, we're going to notice that we actually have two F of X's for the same X. This is not a function. Because the contradiction we have here, he has notes. Yeah, I have notes. Don't worry, Jack. It's fine. Are you subjecting yourself to this for class or personal venture? It's a personal venture. It's fine. But you'll notice here that that fact that we had here, where each X has a unique, each X has some F of X, but not like has a unique F of X. Sorry. Since this X has two different F of X values, that's impossible. It can't happen with respect to set theory. It's impossible. This won't happen. This is not a function. Okay. However, if we have X where like we have a bunch of like values here, 4, and let's say we have 5, no, let's say we have 3, like usual. And then we have like 4 F of X values. And we just pair them up like this, leaving this one like empty. We call this an injective function, okay? Or a one-to-one function, right? It's bringing you back to high school, not gonna lie. Oh my gosh. But yeah, an injective function is one where every x has an f of x. Okay. Ooh. Hello, howdy. Asking Naklavar. Howdy, howdy. Thank you so much for the follow. I'm Volpy, and we're here having a chill old time today, staying wholesome with an S to Risk. Thank you so much for popping by. How are you doing today? So next up, we're going to be talking about the next type of function, which is if we have x and f of x, we're going to have 4 right here and 3. And the thing that we're trying to point out here is that we can actually have 2 x's have the same f of x. So we call this a surjective function, or an onto function. The reason why we use these terms one-to-one and onto is because onto is you basically take x and you're superimposing it onto f of x. Meanwhile, one-to-one means that all of the f of x, or sorry, there's a correlation, direct correlation, 1 x for each f of x. Sorry. This should be all f of x have an x. What's called, bro? I'm dumb. F of x, and then this should be. Oh my gosh, bro! I'm dying here, bro. What? Okay, this is fine. F of x have 1 x, and surjective is f of x have some x. So basically, you're simply proposing the x onto f of x. The next one here is bijective, which is x f of x, and we can just have 3 points here. 1, 2, 3. Move that one up there, this one down here, and this one down here. And this is injective and surjective. So this is a bijective. Basically, you can reverse this type of function because it is injective and surjective. So let's talk about how we are like trying to figure out why a bijective function is reversible, okay? So why a bijective function is an injective and surjective function if it is reversible. There's a dual implication here that you can prove yourself if you want. It's really fine. But if a bijective function is reversible, then that means that every f of x has a unique x, okay? Because we want to be able to go f of x goes to x from some relation, and then x goes to f of x. So basically, all f of x need to have some x for this relation here to work. And then for this relation here to work, the f of x need to have exactly 1 x. So otherwise we get a contradiction with our like set x not being unique. It's set theory, you know, whatever. So yeah, a bijective function is injective and surjective, and also reversible. Cool. That's types of functions we got. Awesome. Well, Now, boys, let's go. Um, from here, we also call X the domain, and we call Y the range. And if we take X union Y is called the field. There we go. And yeah, that's awesome. Excellent. So for our relation R, we're going to be using our Y and X right now. For relation R, the image of a set under R is the subset of elements that can be formed from there. So basically, if you take an for relation R, if we take an injective or a set and like perform an injective function on it, we get the image. Image is the subset of Y formed. Cool. And then if we surject on Y, the kernel is the subset of X formed. So this is what an image and kernel are. Yeah, there we go. Excellent. We can combine relations together, and you can do some cool like proofs that talk about, oh, if you put an injective function on a surjective function, is it injective or surjective, and so on and so forth. Those are really fun proofs to do if you ever have like extra time. But at the same time, it's not something I'm gonna really go into. However, I don't really know if I should talk about that. That's a bit extra now. You can combine functions. Oh my god! I can't believe so romantic for us. So romantic. Oh my gosh, so romantic. Of course, very very pretty. Oh my god. Fuck. Let's use a relation now. Okay, let's use a relation. You know, now that we have our natural numbers, let's use a relation. So let's consider a relation that's going to help us form the integers. Oh boy. All right. So let's try a relation to form Z. All right. Add ship to relation. I'm still damn excellent. Sorry, it's actually Archimedes ship or something. So like, is it really the same ship after replacing everything? I don't know. So let's try a relationship where we take for each n, so for all n element of n, let's try using our negative relation. So what we're going to do is for all n element of n, we have that n, sorry, r of n equals 0 minus n. All right. So this right here is going to give us a certain set of values of, for all of these n, if we have n equals 0, then we get 0. If we have n equals 1, we get -1, we get -2, we get -3, we get -4, etc. Sorry. All right, cool. So if we take this relation of n, and then we union that to the natural numbers, then what do we get here? We get z, our integers. This is fun. We've formed the integers now. We can now go, now use like our negative infinity to infinity. So -1, 2, -1, 0, 1, 2. We have both infinities now. Okay, that's awesome. That's great. We have our infinities. Let's try using, I don't know, q. So our rational numbers using we want to use z. Yeah, that's the one. Boom. Then for all, let's say a and b element of z such that b is not equal to 0, then relation of a comma b, so this is a binary relation, remember, equals a over b. Cool. Now we have every possible numerator from 0 all the way up into infinity, and every possible denominator from 1 to infinity or -1 to infinity kind of vibe. And this is sufficient to say that this means that if we take r of a, b, sorry, this is the image. Image of RAB equals this. Our rational numbers. So now have rational numbers. We did it, guys. All right. Well, now we've got a fun situation here because what's the fun what do we know about rational numbers? Okay, so rational numbers can be formed by a fraction, which means that numbers that aren't rational need to fill in those little gaps in between. So the thing that we do for this step is basically show that two adjacent numbers can't be rational, two adjacent numbers can't be irrational. I don't remember the proof. Oh my god, this is actually an important proof. I need to look this up. Yeah, we can't do much with this. We can't get the irrationals yet. Oh, this is so annoying because we can't get the irrationals, which means we can't get the reals. Oh. Okay. Let's go to the sacred moment. It is time, y'all, for epsilon delta. Specifically, we're using epsilon proofs, which means we need to talk about sequences. So, all right, boys. All right, boys. All right, boys. We got this. Okay, this is fine. 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 This is whatever. This is cool. We can do that. Oh my god. Oh my god. So when we are talking about differences between numbers, we consider that for two numbers that are different, let's call them, here, I'm just going to write. So if we have two different numbers, let's say int numbers, x1 and x2, then we know that x1 and x2 are not equal. Cool? That is logically consistent, because if they're different numbers, then they're not equal. This means that either x1 is greater than x2, or x1 is less than x2. This is logical here, okay? However, there should be some space between them there should be some space between them, basically. There has to be some space between them. So what we want to do is try and define what that space is. So, for example, if we have the difference between these numbers, we're going to consider something called God, bro. I'm missing one thing. Okay. We have a thing called the triangle inequality. Okay. Basically, I will hydrate in just a second. I just need to write my thoughts, okay? All right, perfect. Around these parts, we try and stay hydrated together. It's just important that you guys stay as happy and healthy as myself. I got some water here today, but I'm always curious what you guys might be drinking. So feel free to join along and let me know. Let's go right ahead. No worries, Vanilla. We can hydrate again when you get back, all right? So the triangle inequality is basically reliant on drawing a triangle. So pretty much what we try and show is that if we have a line A and we have a line, what's called B, and this line is going to be A plus B because we're using it in a vector format, okay? So what we try and show is that this length of the line E plus B, which we denote by a, what's it called, absolute value symbol, is going to be less than or equal to the length of A plus the length of B. Basically, by drawing the triangle, we can show that there must be like some deviation up from A to like some height like H, and then some deviation from B. So this H is adding extra distance. And the only time when equality is preserved is when there is no angle here. Basically, if this angle is 0, then A plus B is equivalent to this A plus this B. Okay. So that's what the triangle inequality is. And what the triangle inequality allows us to say is we can say that this A plus B, this number right here, can actually be written more as a, because we know the equality doesn't hold in this left side, the equality of x1 plus x2 will not hold since they're different numbers. Then we can actually describe this with, if we suppose some epsilon greater than 0, epsilon greater than 0, then we have that the difference between these 2 points, it doesn't matter which one it is. We just matter that one is larger than the other. X1 minus x2 is less than this epsilon. Okay? Because we basically need to find a large enough epsilon to encase the difference between x1 and x2, that space in the middle. And so the space in the middle is denoted by the distance between x1 and x2. And we know that that distance is non-zero because if it was 0, then x1 and x2 would have to be equal, and they aren't. Okay? So this gives us a fun situation here where we have x1 minus x2 is less than epsilon. However, as a consequence of this, sorry, let me think real quick. Oh my God, really, Fables? No, you. Fuck. Ah. Oh my gosh, I need to remember how to form the not rational numbers. It happens, Vanilla. It's fine. Ugh. This will come up later. This will come up later. We're gonna go back because I realize there's a way we can do this. Okay. So fundamentally, what's it called? Numbers that can be divided perfectly a over b are going to be a either terminating or non-terminating what's called number. But if it is non-terminating, then it must be also non-recursive or non-repeating for like some term. So we need like some subsequence, like I don't know, like for example, if we have like 1 over 3, this is equal to like 0.3333, but we can select a subsequence 3, and then like just like repeat it over and over again. Okay, that's the kind of vibe we're going for. But if we take those values that aren't possible to like repeat, sorry, are not q. So we take a relation for all a naught, a1, a2, a dot 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 element of z, sorry, of natural numbers. Comma c element of -1 and 1. Then we have a relation of c a naught a1 dot 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 that is equal to c times of a naught plus a1 times oh god, I don't need that many terms. Okay, that's fine. This is fine. Perfect. Because we have all of our non-repeating numbers that go up to infinity. So it's actually just like literally taking a naught and n. And then we basically just say, okay, well, we take all of these. So c times a naught. And then if we take the image of r of c a naught, and then exclude the elements of q, and that'll be equal to r naught q. There we go. Okay, perfect. And it's a times a1. Yeah, I do need a1. Okay. Times 10 to the negative a1. There we go. This will form everything we need. Okay, this is fine. We got a relation. And then basically we can form R by saying Q union R not Q basically says that everything that's in Q and everything that's in R without Q combined together make R. Perfect. Okay. We have our real numbers. Let's go. We have real numbers, guys. We have real numbers. All right. Well, this will be a good point. We did it. That is enough math to form the real numbers, and that is good. That is fine. We did it. Fuck yeah. Okay. So yeah, these relations help us figure out like these numbers. Okay. Excellent. Hydrolux Draws, thank you so much for the follow. Howdy, howdy. I'm Volpe, and we're here having a chill old time today. Staying wholesome with an ass to risk. Thank you so much for popping by. How are you doing today? All right. We did it. My brain, I'm gonna have to like go over notes properly and fully next time, but we have gone through enough set theory. We're not gonna be talking too much about equivalence classes, partitions, or ordering in like different means, because we don't really need to talk too much about the axiom of choice yet. And that'll come up later. It's not really a big deal. The most important thing about like what we're discussing now is that we've just reached the point where, all right, we know enough set theory that we've defined our number systems that we're working with. We understand what a relation is. We understand what a function is. So now we can actually discuss calculus. We can discuss, what's it called? Limits. And more importantly, we can discuss sequences and different types of analyses of sequences and subsequences, convergence, that kind of thing. Which I think is really the fun part about like the beginning of calculus, where you're learning it, like, oh, what causes a sequence or a series to converge? Why do some things do and some things don't, and so on and so forth. And then by the end of that, we'll have like some fundamental knowledge to get the fundamental theory of calculus. Yes. Hey, I saw you doing math and had to stop and see. Yes. Yes, Navy, we did it. We got the real numbers. But yeah, so basically stuff that's going to be coming up next, if I pull up my notes and stuff. So we have discussed different types of functions. We've discussed induction, and we've discussed partially on Boolean arithmetic, but we don't really need to worry about it. Hello, Agent. How's it going? So we talked about absolute values, and we've very partially touched on the triangle inequality up here. With that triangle inequality, we're going to be talking about the least upper bound property, as well as the Archimedean property. And then from there, we're going to be talking about sequences, limits of sequences, because limits are something that we need to like discuss. We might discuss Heron's algorithm if I have time, because that's really good to discuss like sequences in general. And then we're going to be talking about arithmetic of sequences. From there, we'll talk about different things like the squeeze theorem, different types of things like the monotone convergence theorem, even the Bolzano-Weierstrass theorem, And then from there we can talk about limit points and Cauchy sequences, which will basically give us the entire background required to talk about limits and continuity. And that'll be fun, because we'll know limits, and of sequences. So if a sequence converges into something, then, you know, sequences in some products are fun. Yes, honestly. And then from there, I think that's going to take an entire day. Like, I think that's an entire stream worth of content of talking about sequences and limits and continuity. And then from there, we can start talking about derivatives, starting with the what's it called when you have like the over h as limit of h is approaches 0? It's some type of like derivative. And then we'll talk about like the actual like derivative rules, things like chain rules and stuff. And like, yeah, it's fine. You remember learning that in discrete math? Yeah, it's all discrete. And then I guess like, what's next? Like mean value theorem, like L'Hopital's, those kinds of things. Extreme value theorem, those types of things. And then at the end, you know, before we talk about integration, we can finally talk about Taylor polynomials because those are really fun. And Taylor's theorem is really cool. We might even touch on big O when we get there, you know? That could be fun. That could be very fun. You know. Yeah. I just need to remember what that like definition of a limit is, or of a derivative. I need to find this. I need to find what h to 0 is. First principles, that's what it's called. First principles. Yep. It's the delta method, yeah. We're going to be using first principles, and that's the important part there. But yeah, no, that's kind of the framework I've got going forward is, yeah, we've reached the point where we now have enough knowledge about numbers and relations that we can talk about calculus without talking about algebra and set theory, which I think is really cool because now we can start talking about cool looking functions. I can go in VR chat and talk about this stuff. Like I can draw functions and describe what's going on. And that is what I was trying to get towards. These definition heavy, like this definition heavy stream is very important for like building towards things. Definitely limit was frustratingly important, but frustrating. Yeah, a little, but like, you know, you talk about epsilons, and then when you start talking about like continuous functions, you start talking about deltas, and then like you're good, easy, boom, got it. All right, but that has been a good point to stop, I think. Possibly. I think that's a good point to stop. So let's get this going on. It is that time. It's been a really long stream. I'm surprised I managed to go this long talking about math, but like, you know, we're here having a good time and vibing and popping and stuff. But then again, it is that time of day. I gotta get going. I gotta get onto like going to the grocery store, starting up my math assignment because I haven't done it and it's due tomorrow night at 11:59, but it's fine. We'll be good. But then again, I really hope you guys have an amazing night and, you know, enjoy yourselves because it's been a really nice time hanging out with you guys. Thank you for all the questions that you've had. Thank you for just tuning in and listening in. Even if you like fell asleep during it, you know, I appreciate you guys popping by and, you know, hanging out while we do some random math. Ayo. Random ass math. But yeah, I'm gonna be popping out of here. We'll probably be reading into Neon, I'd suppose, just because, you know, Neon will hate me for talking about math, but that's fine. Rest haven't heard of him in a long time. Had to stop by again. Absolutely, of course. Thank you so much for stopping by, Navy. And thank you for all the subs you've given me in random servers and stuff. It's cool. So sharing your knowledge with us. Yeah, absolutely. Be sure to take care, you guys. But yeah, stay by for some extra tales for the raid. But otherwise, I hope you guys have an amazing night and enjoy yourselves. Ciao, ciao, y'all. I'll see you around later.